Kuzuzangpo, Bhutan e-learning project welcomes children to this lesson. I am Funso from YHS and I will be taking you through the physics lesson for Key Stage 5, that is classes 11 and 12. But today I will be taking you all through class 11 physics on the topic equation of kinematics. So before we really go into this equation of kinematics, let us first have some recapitulation of what you have learned in class 9. You all have learned what is displacement time graph, what is velocity time graph. So I will be taking you through a displacement time graph and what does this displacement time graph represents. Now you can see this displacement time graph, a simple graph here where we can clearly see that an object is moving or the object is into motion, and as and when that object travels equal distance in equal interval of time, we say that the object is in uniform motion. So when we actually calculate the slope of that uniform motion given in the displacement time graph, we will actually get velocity. So the example is also given here where slope is equals to rise over run, which is equals to, we have considered the displacement between 20 to 40 meter. So after calculating the slope, we get 10 meter per second, and that 10 meter per second is nothing but it is the velocity of the object. Next, we will go through this velocity time graph. Now this velocity time graph and displacement time graph, this is just a recapitulation of what you have already learned in class 9. So I'm just running through this because we need this information and this idea when we actually do the equation of kinematics. So velocity, basically it talks about the rate of change of displacement, and when we consider the graph of a velocity time graph, it actually shows that the slope of a velocity time graph is going to give us the acceleration, and we will also be looking into one example whereby we will be able to see that the slope is actually giving us the acceleration. And we will also be looking into another example whereby we will be calculating the area that is covered by the velocity time graph, where the area covered will actually give us the displacement of the object into motion whenever it is in motion. So let us look at one example here where you can clearly see on the screen that it is velocity time graph, and this velocity time graph is again for a uniform motion. Now uniform motion, as you already know, uniform motion, whenever the object covers equal distance in equal interval of time, it will always give us the uniform motion. So for a uniform motion, it will always give us a linear velocity time graph. So when we consider that linear velocity time graph, and if we calculate the slope, we get the acceleration, and you can clearly see the example here. And if we calculate the area covered under, or the area covered by the curve in this velocity time graph, we will basically get displacement. Now this velocity time graph and displacement time graph, we are doing it, or I'm showing this right now so that you can recapitulate on what you have already done, because this information is required when we actually do the equation of kinematics. Okay. Now let us get into the real content of this presentation, and it is about equation of kinematics. Now equation of kinematics, let's imagine, okay, let's say a boy is running on a straight path. So whenever a boy is running on a straight path, the boy is going to have some velocity, and if the boy has a velocity, the boy is going to have acceleration because the boy is going to accelerate, and as and when the boy accelerates, the boy is going to cover a certain amount of distance, and in order to cover that distance, the boy is going to take certain amount of time. So usually whenever the boy travels having certain velocity, having certain amount of acceleration, covering certain distance in a certain interval of time, we actually relate these velocities, displacements, time taken, and the acceleration using a relation, and that relation is called as equation of kinematics. So equation of kinematics, basically we define this equation of kinematics usually for a uniformly accelerated motion. So for a uniformly accelerated motion, the equations which relate displacement, time taken, initial velocity, final velocity and acceleration is known as equation of kinematics. So basically there are 3 equations of kinematics, and these are the 3 equations of kinematics, where we have the first equation, v is equals to u plus at. Second equation, v square minus u square is equals to 2ax, x is equals to ut plus half at square. So today in this lesson we are going to derive these 3 equations using graphical method. Now there is again another method where we can derive these 3 equations, and that method we call it as calculus method. But in this presentation I will be using graphical method because this is for a uniformly accelerated motion. Whereas if you are going to derive these 3 equations for a non-uniform motion, we can also use the calculus method. But today I will be taking you through the derivation of these 3 equations using graphical method with certain assumptions. So we are going to use this graph, and we are going to assume certain things, and finally we will be coming to the 3 kinematic equations. So you can clearly see now this is the velocity time graph, and in this graph you can see that or let us assume that a particle is in a uniform motion. So let us assume that a particle is initially moving with some initial velocity of u, and the particle reaches to a certain point, or it covers a certain distance, and when it reaches that distance, it has a velocity v. So we have u as initial velocity, v as final velocity, and let us assume that the time taken by the body or the particle to start with u and complete its journey with v as t seconds. And we will also assume that the body or the particle has an acceleration of a, and it covers a displacement of x. So we have the variables here. First one is the displacement traveled, x. Then second one is the acceleration of the body. Then the third one is the time taken, which we are now going to consider it as t seconds. And it has its initial velocity u and its final velocity v, using the graph which is on the screen here. So in the previous presentation, you all have now seen that velocity time graph, or from the velocity time graph, if we calculate the slope of the linear graph, we actually get the acceleration. So we are going to use that concept here, and we are going to now calculate the slope of the line AB here. So when we calculate the slope of line AB, slope will actually give us the acceleration. So our acceleration A will be actually equal to line AB. And how do we calculate the slope here? It is rise over run. So A is equals to rise here and run. So here, by looking at the graph AB, we can clearly see that the rise here is BC and the run here is AC. So rise here is BC and the run is AC, and BC is V minus U. So we have V minus U, and AC is the time taken, T. So we have A here. Now just rearranging the variables, we will finally get V is equals to U plus AT, which is our first equation of kinematics. Okay, so we'll just take some variables from this equation, okay, because we will need this equation later when we derive the 2 other kinematic equations. So let us first take BC, which is actually equal to V minus U as AT. Okay, let's keep this as equation number 2, and T from the same equation, we will take T is equals to v minus u divided by a. Let's keep this as equation number 3. So, we will be using these many ideas to derive the next two kinematic equations. Okay, so to proceed with the second kinematic equations, we will now consider another concept which we have learned in the previous presentation, that from the velocity time graph, if we calculate the area covered by the graph, we actually get the displacement. So, here we are actually going to calculate the displacement here, and we have already considered the displacement as x. So, x, which is the displacement here, is going to give us by calculating the area of the curve under VT graph. And here the area covered under this VT graph is actually in a shape of a trapezium, where you can see the trapezium shape is O, A, B and D. So, here area of a trapezium O, A, B, D. Now, we are going to do this displacement in two different ways. One, by dividing this trapezium shape into two, and another one by calculating the area of the trapezium itself. Now, first let us do it by dividing this trapezium into two shapes, that is, we have area of a rectangle plus we have area of the triangle here. So, how do we calculate the area of a rectangle? Our area of the rectangle here is OACD. So, area of a rectangle, length into breadth, our length is OD times our breadth here is CD, plus area of a triangle, the triangle is AB and C, ABC triangle, and we can clearly see that ABC is a right angle triangle. So, the formula to calculate the area of a right angle triangle is half times base times height, where base here is BC and the height is AC. So, BC is BC times the height is AC. Okay. So, our OD basically from the graph it is T, then from the graph CD is U plus half BC. So, now BC, we will take this BC as AT from the previous equation, where we have seen that BC is actually equal to AT. So, BC is AT times our AC is T. So, we will get x equals to, just rearrange again, UT plus half AT square, which is our second kinematic equation. So, let us keep this as equation number 4. Okay. Now, we are left with the last equation here, and to derive the last kinematic equation, as mentioned earlier, we can calculate the displacement in two different ways. One, by dividing this trapezium shape into two different shapes, and by just calculating the area of the trapezium itself. So, if you just calculate the area of the trapezium, area of trapezium OABD, the formula to calculate the area of trapezium is half times the sum of two parallel lines here, and the two parallel lines we can see is OA and BD. So, OA plus BD times the height here, and the height here is AC. Okay. Now, half our OA is U and BD is V. Then we have AC is T. Okay. Now, we will play with this equation from the one which we have already considered in from our first equation. So, from our first equation, we have taken T, which is the time taken, as V minus U divided by A. So, if you take this T as V minus U divided by A from the first equation, we get our displacement x as half V plus U, V minus U divided by A. Okay, so let's rearrange this. 1 by 2a v plus u v minus u. Okay, now this v plus u and v minus u, it's very familiar. It's a mathematical rule where we say a plus b and times a minus b is equal to a square minus b square. So we are going to apply this rule here in v plus u and v minus u. So this v plus u and v minus u is same as writing v square minus u square. Okay, so after applying this rule in our displacement, we finally get our x as 1 by 2a v square minus u square. Or let us rearrange this. So we get v square minus u square is equals to 2ax, which is our required third equation of kinematics. So we are done with this derivation of the equation of kinematics. Now, where do we actually apply this kinematic equation is we don't have to dig every loops and corners to find the examples or real life application of these kinematic equations. Whenever an object is into motion, any object or any body, whenever they are into motion, that object will always be governed by these three kinematic equations, where we have the first equation v equals to u plus at, second equation x equals to ut plus half at square, and the third equation v square minus u square equals to 2ax. Okay, just to show you all how to use these equations or how to apply these equations. When can we use this equation? Why do we use this equation, or in which kind of question we use this equation? I have one example here. I'll show you the example, and I have a question for you as well. But before the question, let me show you how do we choose the equation and how do we calculate the quantity using these equations. Okay, Jigme accelerated from rest at a rate of 6 meter per second square for a time of 4.1 seconds. Determine the displacement of Jigme's car during this time period. So this is the question, a numerical question here, and we will now be using any one of the equation of kinematic equations in solving this question. Now, before we solve the question or before we solve any numerical question, the first thing that we do is we jot down the given quantities or the value of given quantities. So we will do the same here. Okay, so first let us jot down the given values. Read the question very carefully. Jigme starts from rest. So if Jimmy starts from rest, Jigme's initial velocity will be 0 meter per second. After the spotlight has turned, or when the spotlight turns green, Jimmy accelerates with acceleration of 6 meter per second square, and Jigme takes a time of 4.1 second. Now we will have to calculate the displacement of Jigme's car. How far Jigme has traveled in a period of 4.1 second when he accelerates at the rate of 6 meter per second square, starting initially with some initial velocity of 0 meter per second. So how to use, or which equation of kinematics to be used in this particular question? Now you can just look at the quantities here. What are the quantities given? So the quantities given here are initial velocity, then we have acceleration, then we have the time taken. So just recapitulate on what you have learned in the derivation, the three equations, and we can use one of the equation where we have u, where we have a, where we have t, but we have to choose the equation in such a way that the equation does not have its final velocity, because we don't have the final velocity given in the question. So by looking at, or by choosing one of the equation from the kinematics equation, if I were you, I will choose x equals to ut plus half at square. So I'll choose this equation. Why? Because I have u here given in the question, I have t, I have acceleration, and I don't have v given in the question. So this equation is perfect for the question. So using this equation, because this question itself is to determine displacement. Displacement means x, and this displacement is equals to ut plus half at square. So after taking the equation, we will just plug in the values of u, a, t, and after we put all the values of u, a and t, we finally get 0 times 4.1 plus 1 by 2, acceleration is 6, then we have time 4.1 square. So after all the calculation, my displacement or the displacement of Mr. Jigme traveling at the rate of 6 meter per second square will be 50.4 meter. So I have the solved part for the given question on the board also, so you can go through this once. I hope it's clear now how to go on with the calculation. Now with this concept of kinematic equation and solving numericals, I have some question for you all as well, and the question is a particle moving with uniform acceleration along a straight line covers a distances a and b in a successive intervals of p and q. What is the acceleration of the particle? As we come to the end of the lesson, let us have some summary of what you have learned. So we started with displacement time graph, then we went through velocity time graph. Now this displacement time graph and velocity time graph we are doing in this presentation just to recapitulate what you have done in class 9. Then we came to equation of kinematics, its definition, and certain assumptions to be taken while deriving the 3 kinematic equations. Then you have also learned which equation to be chosen for what kind of numerical questions. Okay, so this is the end of my lesson. Thank you for attending the lesson. We'll see you in my next lesson.